Efficient and comfortable haptic retargeting with reset point optimization. Haptic retargeting is a technique that provides passive haptic feedback to the user by mapping multiple virtual objects to a single physical object by tricking human perception. It enhances the user's VR immersion through passive haptics. When the retargeting gain between the physical hand and the virtual hand exceeds the threshold, the hand needs to be moved to a fixed position for resetting. To further enhance the haptic retargeting usage experience, Matthews et al. Proposed the adaptive reset method. The green sphere in the video is the point reset position, and the green face is the threshold reset position. The method is optimized for the reset position, reducing additional hand movement. Siming et al. Proposed the proxy importance method, which can greatly reduce the number of resets and improve the efficiency. This method sets the reset point at the corner of the table. However, none of these works considered the user's comfort during the reset operation. To address this problem, we propose efficient and comfortable haptic retargeting with reset point optimization. The orange cubes indicate reset point, whose position is calculated by the algorithm. Our method introduces the concepts of ergonomics and psychology to haptic retargeting for the first time, and enables users to use retargeting techniques more comfortably and efficiently. Our method has 4 steps: map construction, candidate reset point initialization, reset point selection, and proxy placement location updating. Based on the RULA lower arm score in ergonomics, we first constructed the RULA score map, which is used to indicate the user's comfort in interacting with different areas, with lower scores indicating greater comfort. Based on the psychological need for people to prefer to move their hand to the side of their dominant hand, we also constructed the dominant hand score map. For example, if the dominant hand is right-handed, moving to the right is more comfortable and has a lower score. Our retargeting system is to move the cube block on a 1.5 meter * 1.5 meter desktop, and the virtual objects will be randomly distributed on virtual planes of equal size. We grid the virtual plane and place a candidate reset point of size 0.1 meter * 0.1 meter every 0.15 meter, totaling 81 candidate reset points. Based on the candidate reset points described above, we propose a reset point selection algorithm. For each reset candidate, we first index the RULA score map to determine the RULA score based on its location, then calculate its distance relative to the physical hand, and the retargeting gain of the physical hand and virtual hand relative to candidate reset points. We add the above values as the total score for the candidate reset points. Finally, we multiply the total score of candidate reset points in the dominant side area by a number less than 1 to make it easier to select. Here is an example of selecting a reset point, where the candidate reset point with the lowest total score is selected as the final reset point. After the reset point selection and reset starts, we use the proxy and position updating algorithms to select a more reasonable physical proxy or placement. In this algorithm, we compute the importance score, the retargeting gain score, and the RULA score for each candidate proxy or placement location. We add up the scores and the one with the lowest score is selected as the final proxy or placement location. Here is an example of updating a physical proxy, where the physical proxy with the lowest total score is selected as the final proxy. We compared the comfort and efficiency of our method with Siming's method and Matthews' method. The method of Siming et al. Does not perform any optimization on the position of the reset point, and sets the reset point fixedly at the corner of the desktop, which satisfies the psychological needs but creates additional hand movement. The point reset and threshold reset methods of Matthews et al. Consider only 2 factors, distance and threshold, which reduces additional hand movement, but fails to satisfy user ergonomically and psychologically needs. Our method is able to set the reset point at an ergonomically and psychologically correct position during reset and is able to minimize additional hand movement. We also updating the physical proxy or placement location when a reset occurs. The video shows only a part of the study, and from the results we see that our method achieves significant improvement of efficiency and comfort. That's all. Thank you for watching.